All right, last recording for machine learning class. This is I'm doing assignment 4, I think. Is it assignment 4? No, assignment 3. Um, this is the assignment. We're first off doing k-means clustering on the Boston data set. So let me show you that k-means. This is pretty straightforward. I didn't bother to comment through all this because I'm going to just show you how it works. Um, Basically, we initialize the means. This is the first data points. Afterwards, we load in the data, and this is all to hash out the eighth parameter is categorical, so it puts it into one hot, and then we're centering and standardizing or normalizing. This basically just goes until the array of means it hasn't changed, and it just pops everything into clusters based on the nearest ones, and then calculates new means. Very, very straightforward. I can run it. I don't think this shows an accuracy because it wasn't requested to, but it does show it's a nice little plot using TSNE, which is it's a method for mapping high dimensional data into lower dimensions. So I set the perplexity to 29 because that seems to give me decently intelligible results. The green and blue, these are the smaller clusters tend to cluster together. Some of the bigger ones, either these are misclassifications or they have outliers or something like that, but they don't classify as neatly. And that happens no matter what I set the perplexity to. If I run it again, it'll generate it as a different model. See, they're kind of roughly in groups, and blue and green usually stay together, but the reds and oranges break apart. So yeah, that's cool. And that's what that plot is, what all this code is, which is ugly as frick, but it's fine. This is for plotting analysis. So this is a decision tree. This is my implementation. Basically, rather than doing the whole node class for an actual tree structure, I defined it using a dictionary that's recursively defined. I'm really tired. It's late. Basically, it's just this optimizes to find the best split. So it finds the proper split location, because this is all we're classifying. We are classifying. Which one is it? We're classifying iris. Okay, so iris, it has, I believe, 4 different parameters, and they're all continuous. So we're finding the optimal splitting point, basically by sorting through each feature that we have in our training data, and then we just go ahead and set its we just see what the optimal splitting point is for the greatest decrease in entropy, which our entropy function is defined down here. It's very straightforward. And then so we take this. I did a train test split here just to kind of get an idea of how accurate it is. I did a 50-50 split, and it comes out 92% accurate, which is not bad. This is actually a pretty solid algorithm. Obviously, the assignment didn't actually say that I had to output anything about the train test accuracy or anything like that, but I wanted to for my own information, and I can get rid of this if you want. I can just boop, and then that's technically what you asked for, which is no output at all. But I felt like giving the accuracy was a little more informative in this case. That's 50% divide. You can do like 90% or whatever. That's actually probably lower with 90% because this badly overfits. But we can do 0.6. Yes, 0.6 gets 97% accuracy. So you can play with how much is training data, how much is testing data, and try to sort out how much is going to overfit. Because decision trees, especially because this will just go until it finds a decision tree that perfectly matches the training data. It's going to overfit a lot if you have really high training data proportion. So then we have our ensemble learning. This is using these three things that I did in an earlier assignment. Logistic regression. I made a couple of edits here for stability. This is just basically to keep these values from exploding. I also increased the number of iterations it runs and the alpha value. The neural network didn't work before because it super underfits. Actually, it just predicts everything to 1, and there's not. This architecture was given to me in the prior assignment, so there's not anything I can do to change it without fundamentally altering what this assignment's supposed to be. So this is basically just a bad model, and this is gonna screw up the ensemble, but it's fine. The ensemble still does pretty okay, just using basically with these two being the only ones that work. The KNN, this wasn't defined as a class, so I mentioned up here I didn't import it because there was nothing to import. I just implemented, basically copy pasted that code back down here with a couple of simple changes to, instead of printing the predictions, just totaled them into a list. But yeah, that's the KNN. And then we do our logistic regression, our neural network. We have all our model definitions and stuff up here, finding the weights and solving for them. Each of them is using 64% or 63% of the training data. And then we just find our accuracy at the end by basically taking the rounded average of these, which is just essentially a simple majority rules voting system between the three models. So we're bagging here. It didn't say whether I had to bag or boost or anything like that, so bagging was just the easiest to implement. Yeah, so we are counting the number of instances, doing our predictions, and it gets like usually 80 or 90, yeah, 92% accurate. Yeah, there you go, 92% accuracy. I get some warnings for overflows, which is why I put in these limits. But yeah, that would do it. So that's gonna be all for this video. Hopefully the assignment is satisfactory. I'm graduating, so I probably won't see you next semester, but it's been a nice class. I'll see you around.